So let's, without further ado, let's go to the final speaker. Juan Luis Vasquez does not need any introduction whatsoever. He's going to talk to us about Healy-Shaw asymptotics for mechanical models of tumor growth.
Thank you all for coming to this event and the last talk in the long series of this week and the long series of the program. I'm very happy. In fact, I like introductions because introductions are usually put the author in better perspective than the talk by the author. But in any case, okay. So the idea is that due to the interest in the models in mathematical biology, there are a number of subjects that are pursued by mathematicians trying to understand how they work, and one of them was this idea of why tumors grow. And this is something I learned many years ago from Avner Friedman, and I didn't do much about it because, well, I was at the time tending to be more analyst than applied. And then all of a sudden we had a project with Benoit Bertam in Paris, who had a parallel, but direction was opposite direction. He was trained as an analyst, and then he decided to work in the more applied parts. He gave a series of lectures in the introductory school in January, and one of the things we did was years ago, he convinced Fernando Quiroz, who is around here, and myself, that there was a problem where we could use techniques that we like, in fact techniques that I learned in Oxford many years ago. So the idea is that there are models of simple free boundary problems and PDEs that could be used reasonably for explaining elements of tumor growth. Tumor growth is very complicated. There are many aspects. I am not reliable in everything you want to know. You have to ask people who really know about the field. In this audience there is Professor Longrop, and I got most of my information from Benoit Bertam in his project. Okay, so the idea is that well, we wrote a detailed paper explaining how the method works, and this is the main contribution of this talk. I will talk about one paper in particular and how it works. So, the understanding of cancer development uses mathematical models and numerical simulations combined with experimental evidence and clinical observations, and since you have been probably in the talk this morning by John Longrop, you know more or less how it works. One of the models that inspired this discussion was initiated around the 70s by Greenspan, and there is a paper where he considers cancer cells multiplication limited by nutrients brought by blood vessels. So there is an explanation of why things move. And the models in this class have two kinds of descriptions. Either do you use dynamics of cell population densities, or you consider geometrical motion. And this idea of geometrical motion was the thing that was very much pursued by Avner Friedman and collaborators, Sway, etc., because it led to the free boundary problems that are so popular in our community. So as a summary of this small introduction, the models introduce something which is called competing for space, and there is a pressure limited growth, because in some sense you explain by introducing a concept of pressure the idea that they are packed, and in some sense this explains why some cells cannot move anymore and they are necrotic in the middle of the tumor. We will see this necrotic thing later. And the descriptions can use cell scale or solid tumors. We want to start with cell scale, and the solid tumor has a tendency to be good for free boundary presentations. And while the cell scale uses diffusions and things like that, so we want to see how to pass to the limit in a simple way. Okay, so the mechanical models say, I'm giving you a paper for reference that I didn't really study very much, but it is the reference that we have to the model we take. So believe me if I say that we took this model from these people. It says that there is a diffusion of the porous medium type, so the velocity of this conservation law is minus gradient of a pressure, and then there is a reaction, and the reaction is rho times, which is the density, a certain function which is the reaction rate. You take initial data, and essentially the model is closed if you say what is the pressure. And then you say that the pressure has two effects. One of them, it appears in the pressure limited growth in the reaction term, where we say that the pressure will, this phi, the rate, the rate per unit rho, will be decreasing with P. So if there is a big pressure, it means that there are so many cells there that they cannot survive because of lack of nutrients. And in fact, the real equations will be a system, but let me simplify the system into this thing that says that phi, or phi, is decreasing with P. And there is a critical P where they cannot grow anymore and just they diffuse, I mean, they are dead. And then if you multiply rho times phi, you get one of these things that are the family of reaction terms related to KPP and combustion problems, and Professor Tu explained in his talks if you were there. Now, the next thing we did, which is probably, well, this is one of the choices that was very well motivated, and it's not the typical thing, because it's really, if you take the rate, the phi, it's really decreasing, bit concave. And the next thing is that since the model, I mean, the idea of the model is that relate the pressure with the density by means of a certain power. So if there is more density, there is more power. And remember that if you have a lot of pressure, then you will begin to have problems with surviving, because the pressure is the difficulty in getting around and having access to the blood vessels that will feed you. Okay, this is the model. And the idea of the model, you just solve this problem, which is a porous medium problem. Okay, so this equation, with you put P equals rho to the m, is the porous medium equation with exponent m plus 1. So the next thing we do is you wrote the equation, okay, with a reaction. This is a porous medium reaction. This is why Benoit came to talk to us. He said, listen, Juan Luis, you should be able to solve this thing. And we said, but it cannot be so easy. He said, no, no, no. Once you solve this thing, we will do something else that is very beautiful. So you write the equation for rho, and then you write the equation for P. The equation for P has this term split into one P Laplacian P, and another one that is gradient P squared, which is very typical of analysis of free boundaries. So when you are on the famous free boundary, you will find in the end P will be 0, P will be 0, and this will be the famous free boundary term that we want to recover. Okay, this is a way of writing it, so there's nothing new. And the thing now is that we want to pass m tends to infinity, and what P was linear with rho and then power with rho, when m is really very, very, very large, it looks like one of these multigraphs, maximal monotone operators. This is the graph which represents P infinity as a function of rho. So rho can go from 0 to 1. We are normalizing rho over rho c with rho c equals 1, so it's rho to the m, and this tends to this graph, right? So you are trying to solve one of these multivalued problems, which in other ways is a way of writing variational inequalities and then free boundary problems. So this is the thing that we are trying to do, passing to the limit. The diffusivity goes to infinity if rho is larger than 1, so everything that rho is larger than 1 will disappear by diffusion. And if rho is less than 1, they will not move, because the diffusion will be degenerate. In fact, you can do models where you let them move a bit even if rho is small. The main problem is that I will saturate at a certain level that I call rho equals 1, the diffusion thing. Everything will move very quickly at the level rho equals 1. And once you do this, then you want to know what is the limit. And when the first thing you say, for some reasons, rho larger than 1 will not exist, so let's assume from the beginning that rho equal or less than 1, because you are assuming super diffusion for rho larger than 1. And then the limit as m tends to infinity is something that I learned more or less in 1982 in Oxford. We were discussing these things about Hillshaw and mesa problems and things like that. And there was in the air at the time. And then there were papers in '86, there was a paper by Elliott, Herrero, King, and Ockendon, that they passed to the limit in the porous medium, no reaction. And they found that in fact what happens is that if you have a certain configuration of the initial rho naught, which is like this diffusion makes it collapse immediately to the level rho equals 1, because it's super diffusion, and it happens in an amount of time epsilon that goes to 0. It's a boundary layer, and once you do that, you have this thing. If you have a tail that was much less than 1, maybe the debris of your collapse will not affect you, but there is this region where the initial data have collapsed. Once you collapse, the solution, once it is collapsed, u0 plus x will be uxt when m tends to infinity for every t. It will not move. So the mesa problem was an idea of explaining the catastrophic effect on the non-compatible data for very fast diffusion. In fact, this is not what we want to do, but this is one of the things that you have to analyze. It was analyzed then very carefully by a number of people, and this is part of the folklore of many conferences in this program, trying to work out the details of the mesa, of the diffusion collapse that we call mesa. In fact, since I'm rather classical myself in this kind of taste, or maybe old-fashioned, okay, I have been working last year for a fractional ablation version of this model, which is very beautiful. And it's not really very difficult, but you have to know where is the new novelty. And fractional ablation is, as you know, replacing the Laplacians in the formulation by fractional ablations, and this is something that is now, it was very popular since 2007 around, and we did lots of that in the program in MSRI. So the idea that I want to do now is something else. Let's eliminate the level of the rho, and let's try to look at the level of the p. Level of rho and level of p are singular levels as p tends to infinity. So instead of looking at what happens here, try to look at what happens here. Rho is already saturated, you don't see the rho anymore, but maybe the p does something. And if you go to the equation I wrote before, then the p has to do something that is the singular limit when m tends to infinity. There are two terms here that have infinite coefficients. Pass the coefficient to the other side and you will get an elliptic equation that looks, eliminate this term, oh my god, eliminate this reaction term and you get p Laplacian p equals 0, Laplacian p equals 0. But on the free boundary you will still get derivative of p with respect to t minus gradient p square equals 0. This is the Hillshaw model. And this idea that passing to the limit on the mesa problem with data that are well prepared for the p and are completely incompatible with the rho scale gives you another limit. This is something we did years ago with Fernando Quiroz and Omar Gil, Uruguayan, and Don Aronson in Minneapolis. We did this analysis, what we call the Hillshaw limit of porous medium when m tends to infinity, and there are two options. Either you go to the mesa or you go to the Hillshaw. Now this was without reaction. You cannot combine the two things because either one or the other. And in this limit of the Hillshaw, there are a number of people working. Let me quote some people who have been working around. Okay, so the idea is, in my problem here, I will get the two things. And this will be the nice idea is that I will pass to the limit in the well-prepared data. With reaction, I will get a mesa, and I will get Hill-Shaw, and there will be free boundary problem, and you will have a spherical propagation of tumors. So we are in the good case of Hill-Shaw, so it doesn't create dendrites, it creates blobs, circular blobs. So let me try to explain to you how to do that. Once you know that you have to do two things in one stroke. The main point is that if you prepare the equation, you can combine the two effects. So we will do some mesa problem, like there, and we'll do some Hill-Shaw problem, and the reaction will be important in explaining that. So let's take off for simplicity that Q is R, or Rn is the same thing. And you can take 0 infinity or 0t. And the conditions on the data is, well, you can take fixed rho. We are not preparing the data for the P. The pressure will appear as an effect of the growth driven by the reaction term, by the fact that cells can multiply, reproduce very quickly. And so you don't need to prepare the data for the P, which will be, the pressure will be stationary and will be a product of the problem. And so you prepare the data so the density of your approximate problem is near a certain density. You can take the same density all the time. And you say that the initial pressure is less than PM, which is the critical pressure for survival. This is the only way that you prepare the data. Another thing we do, because we have to do complete proofs. People in applied math says, why do you do it, Juan Luis? It makes your life miserable. But on the other hand, there are lots of friends who like the proofs. So we had to prepare this thing with derivatives control, and this is to have estimates in bounded variation spaces. And I tried to eliminate it, and Benoit Pertam said, you never do that in a paper with me. It will have bounded variation. So it has bounded variation. But once I give this lecture, I will try to eliminate bounded variation. Now let me tell you what are the pictures. One of the pictures is here. I mean, I put the two pictures together for rho and P. This is an intermediate picture where the rho, M is not very large, M5 here, and there is a certain density that tries to be saturated already. Rho is more or less like a bell shape, but here is more or less 1. And the pressure has begun to react as a power. And M is equals 5, so the power of this concave has already a bell-shaped form. And next thing is the rho is more or less 1 here. But of course, if M is not so near to 1, if you take a power, then the pressure is smaller. So saturation when M is very large has to be very, very saturated to generate a pressure, because otherwise there is no pressure for rho less than 1 in the limit. So it is a problem of limits. Now this is pictures produced by people in Paris, and this is an evolution thing where you get a certain it is the system for M large, so there is in principle no difficulty in solving the system. The only point is that we are using M equals 40, which is okay. And then you have a small blob of material, and this is the small pressure, because it's touching but not so much. You have to raise this difference to the power 40. And then this thing is already beginning to move out, and you see that the pressure, because here is more or less 1. And then this thing has done further movement, it's approaching a bit more, and you get more pressure, and this is the beginning of the traveling wave. It will travel in both directions, and the pressure will be a parabola solving the elliptic equation, Laplacian P plus phi of P equals 0. So this is it. This is what we want to see. And the theorem says that if you assume that the initial data converge, as we are assuming everything else, then the densities converge to something that is in L1 and BV, the pressures converge to something that is in BV, the densities will be in the accepted range 0 less than rho less than 1, because otherwise there is no mesa. and the pressures will be below the pressure where everything is killed. So of course the pressure will never be larger than PM, because if pressure is larger than PM, there is no reaction. So this is what says that the pressure will be completely ineffective. Since the gradient of pressure is important in the survival of the species, this means that there will be necrotic part. Oh. Okay, so put the clock back. I will do it. We do the whole thing over in Spanish and Serbo-Croatian. Okay. Okay. So, assuming that the public in the audience out there believes the beginning of this talk, let's go on. So, the public here has believed the rest. Let me continue. Thank you. Okay. So the point is, what is the limit? The limit satisfies an equation where m tends to infinity, and this is the thing that I'm writing, because I was writing something like rho t equals Laplacian of rho gradient p plus rho phi of p. But it seems that when rho when m tends to infinity, you have to look at the terms that you are taking here, and this rho will be rho infinity, and this rho will be rho infinity, and this thing, since p is a power rho to the m, it means that rho gradient p is equivalent to gradient p. It's the difference between the power m and the power m plus 1. So you pass to the limit, and in fact you get rid of this rho that was a factor in the equation. So this is the final equation that combines two variables. And the point is that if you look at the equation in this way, maybe it doesn't have any uniqueness. And then you say, no, but p has to be in the graph of rho. Either rho is between 0 and 1, and then p is 0, or rho equals 1, and then p satisfies the equation. So the point of the rest of the talk is trying to convince you that this equation that we are writing here allows you to see the Hill-Shaw problem and the uniqueness. Let me go for the Hill-Shaw problem. Remember, Hill-Shaw is something that you see in the p variable. So you write again the equation for p and try to pass to the limit in p, right? And then you discover that you will get a complementarity formula when p tends to infinity, when n tends to infinity, because n minus 1 kills these two terms. So you will be able to prove the formula that characterizes the solutions of the Hill-Shaw problem inside. And you only need to know if this formula makes sense with our regularity, because you are multiplying p, which is not a very good function, but gradient p, which is a measure. But what you do is you use the weak formulation, and the weak formulation allows you to integrate and get this thing. Now, this is a bad guy in conservation laws, and we are risking to lose all the diffusion, but it is possible in the framework of our assumptions to prove that the gradients converge in L2. And you have to do some computations about monotone operators to prove the convergence of the gradients. And this is what you cannot do in conservation laws. And this is where you have so many problems. In this case, you use the parabolicity a bit to be able to prove the convergence of this thing. Once you prove the convergence of this thing has a sense perfectly almost everywhere, and you can prove that this complementarity formula is true. But then, Oh, and there is improving these things, we still have a problem with the derivative of time with respect to p that is maybe a measure also. And then what you do is that there is a number of tricks in the regularity theory for degenerate parabolic equations. One of them is replacing derivatives by incremental quotients or by Steklov means. There is a technique that is in the paper, and you go on and you prove that the complementarity formula is true. So this seems to be the Hill-Shaw problem. Now, since it is not classical, I cannot say that on the free boundary, I don't know where it is, you have the conditions to get uniqueness. So there's the problem of knowing what will happen. In fact, the free boundary problem in the classical formulation, if I was able to prove it, will be that there is a number of points where p is positive and rho is 1. This is the saturation condition, and it is because there is this graph. And the next thing you say is that in the positivity part, p is positive, and the complementarity will say that gradient p is phi of p, which is the typical quasi-static reaction for p. This is what generates the pressure that kills the inside of the tumor. And then the free boundary conditions will be this, so you get a free boundary problem. Now, this is not true. It's very nice. It's only true in some particular situations where you get data that are very black and white. But we have data, like in the MESA problem, that have a certain part at the beginning in the form of tails. And these tails in the initial configuration are what you call precancer zones. So there are a certain density of bad cells around who are not activated. They will be activated by the coming pressure from the Hill-Shaw model. And the idea is, can you make them, combine them in the system? In fact, I was solving the equation by assuming that you could have a part of my rho that is a tail less than 1. It takes some time, this front takes some time in coming, while the front didn't come, nothing happens to the tails. So how do you prove this thing? Okay, one of the things you prove is that even if you assume classical conditions, if you have outside a certain pressure, a certain density in the precancer zone, this density, according to the equation, we have an equation that was rho t equals Laplacian of rho gradient p plus rho phi of p. If you are assuming that you are in the precancer zone, the p will be 0, but you still have reaction. So the precancer zone is still feeding and reproducing, and the only thing it needs is the wave coming to them. So you have a problem that we have identified in this work with Hill and Quiroz, that is that in the precancer zone you get an ordinary differential equation, and in fact then the velocity is not the gradient, but the gradient divided by the effective latent jump, the latent jump. There is a jump. The jump is between rho bar and 1, which is the limit. So if you are very close to being activated, then the velocity is very large. And this is what happens in Hill-Shaw, when instead of having the enthalpy, you are heating the ice to be the Massey region almost to the enthalpy that allows you to change phase. So this is a change that introduces the combination of the two regions. There are two regions that in the weak formulation you cannot separate. One of them is expanding in the Hill-Shaw way, another one is growing in the stationary way in space and growing in time. How do you put them together? Solving the limit problem for the equation. And in fact, how do you solve the problem? Just by solving the problem for m very large and passing to the limit. You solve it for m equals 40 and you can see the things. This is what they did in the simulations. And now let me give you an idea of what you do to prove these things. There are L infinity estimates. We're using technology that is long and cumbersome, but is well known by people in the area. One of them is you use standard comparison arguments because the maximum principle works for this equation. You prove that there are bounds for the rho and there are bounds for the p. And then you prove the LE1 estimates, this is the famous contraction estimate. Since there is reaction, it grows exponentially with time, but this is essentially the contraction in L1 for degenerate semigroups. And then you get estimates like this. You get the estimate for P by combining the fact that P is bounded and is a power of rho. And the two things give you that then P is also L1. And this is important in passing to the limit in L1. And then the trick to deal with the derivatives is that there is this magic, what we call Aronson-Bendilan type estimates, the people in geometry call Li-Yau estimates. Something in this flow is almost convex. And the something in this case is this combination. So you call it W, and you work, we have been working maybe 1 month, right, of trying different W's. And then one of them is good to prove that this thing is bounded below by a certain exponent, whatever means that Laplacian is not such a bad guy, the gradient is more or less compact. Functions are bounded, and the Laplacian is bounded below, more or less you can do it. And then you have to write the equation for W to prove that this thing, there is a subsolution that is explicit. This is technique. It's enormously long technique, and sometimes you don't know where you get the equation, the function that you have to compute using maximum principle. And this reminds me of things that we see when you do blow up for free boundary problems, that there is something that has maximum principle or has a monotonicity formula. Here the monotonicity formula, we don't have it, so we use maximum principle on derivatives. And then you pass to the limit in the pressure equation, you get the exponents, and what happens in the limit for this simple model is what really makes things very easy to prove things. It is that in the end, the density is increasing and the pressure is increasing for this reaction model. So everything is monotone increasing for every x in time. And this, of course, makes your life very easy from now. And then the rest of the proof is making the estimates by using the fact that you are not working with strange measures, you are working with positive measures. And there is lots of work that is done in the paper. Some of the things are relatively easy, but all of them is, you know, the people who know how to do it. For instance, you have to prove this, you multiply by the sign, you use Kato's inequality, the convergence in L1 you use is the estimates in W1 log, control of mass. This is the proof that the initial data are taken. If the initial data are not taken, then you have a problem in believing what you are doing, because maybe you have one of these dramatic collapses when t is near 0. In that case, we don't have that, because we have prepared the data not to have this strange part. And then you prove that there is finite propagation. Now, finite propagation is now very easy, because in fact we are doing a variation of the Hill-Shaw model, and there is a super solution for the Hill-Shaw model that is so easy. It does not depend on this term very much, so you make a calculations, and you see that there is this parabola that expands with time and explains how the pressure is expanding around. So you do this thing, and the problem is uniqueness. So I have constructed a model of weak solutions for the limit of porous medium with reaction that combines the growth of the densities that are small in the tails with this Hill-Shaw model in the middle. Can you prove uniqueness? And then uniqueness is something that is difficult, because P is not a Lipschitz function. We cannot prove this. And in fact, there are these things that if you have a, oh my God, if you have a blob here of material, and it has a certain pressure, and the pressure is like this, and you find again another blob that meets the previous blob here, when you put the two blobs together, then the pressure will satisfy the Laplacian equation in the whole union of the two. So there is incredible discontinuity in the behavior of the pressure at the meeting points. And you will tell me this is a phenomenon in one dimension, because in two dimensions you get two balls that collide, and since the collapse is not so big, there is no big jump. But in any case, the pressure will be discontinuous in some sense. So you cannot prove that the pressure is a nice function. And what you do is something that is called, it's very interesting, called the duality method. You write the equation and you multiply by a test function, and then the Laplacian will go here. This is the phi and this is it, and then you would say you take out by brute force this factor out. So in the case where you had here u1 rho1 minus rho2, then you take this factor out and you get this quotient, and this is a coefficient that is less than 1 and larger than 0. In the factor that was the Laplacian, you will have P1 minus P2, and you take out this factor and you get this quotient, but it's still less than 1. So you write the dual equation as an equation with probably bad coefficients, but they are bounded. And it's an elliptic degenerate equation. And if you are able to solve it, then what you find is that you can put 0 here, and then okay, if you solve it with 0, then there is nothing to prove, because the solution will be 0. Solve it equals f, and then you say that for every f, this thing, the equation, the corresponding equation, will have 0 equals rho1 minus rho2 plus p1 minus p2. So it proves that p1 minus rho1 minus rho2 plus p1 minus p2 has to be 0. I think I'm a bit confused in explaining you that, but this is the duality method that is so much used in hyperbolic problems. Was adapted to parabolic problems by Kalashnikov in Moscow, and then by Crandall and company. So this is what we do. You take this duality equals something that is g is the variable, and you put it in the formula, and in the end you find that this is 0, and since g is any forcing term, you can solve this equation for any forcing term. Rho1 minus rho2 is 0. So this proves uniqueness. And this is the end of the proof that there is a model that combines Hill-Shaw with porous medium, the precancer and the cancer zone. And the next thing I will do is try to tell you that there is a system more realistic, where instead of saying that everything is independent of the nutrients, you will tell how the cells survive. So this is the same model, but then the reaction, I mean the birth rate or the conservation rate of the cells depends on the pressure and on the concentration. It will depend negatively with the pressure and increasingly with the concentration. Has double monotonicity like all the good systems. And the concentration will solve a very simple linear equation where the nutrients disappear because of the thing. You can put psi more or less like phi, because what disappears from here gets here. And you say that the nutrients away from the cells go to a constant at infinity, because you don't want to solve it in a bounded domain. So this is the assumptions on the phi. It decreases with p and it increases with c, and there is a value for which there is no reaction. And about this consumption of nutrients, if p is larger, you consume less. If the concentration is larger, you consume more, and there is a value for 0 that is 0. And what you want to prove is that if the assumptions on the data allow you to have a well-prepared problem, and look at these beastly things on the initial data. Okay. And then you can prove that the system converges to the limit, and look at the same formulation of the limit problem as implicit complementarity formula. There is this thing that replaces the value of the complementarity formula, and then you have a combined equation that is simpler, one of these linear reaction equations for C, I mean semi-linear. And of course you know that P has to be long to this Hooke's graph with respect to rho, this thing here. And you get, of course, finite speed of propagation for the cells, not for the nutrients. The nutrients solve an elliptic equation, a parabolic equation. And you prove uniqueness by complementary, by the duality method. And this is a nightmare that we had decided not to put it. But then, I don't know who was impossible, maybe Fernando. So we had to work extra to get the proof of uniqueness for the system, which is really difficult. Now, let me explain now a bit about what happens if you start this evolution and you let it go. Then you want to see something that they took from some pictures, numerical experiments, that is that the density will be 1 for a long distance and then go to 0. This is the remainder distance, maybe the tail. Here they didn't take any tail. And this is the pressure formation. The pressure formation will be rounded near the tip because you solve Laplacian P equals minus constant. So it's like a parabola. But then when P is like the critical P, the reaction is 0, the Laplacian is 0, and it's constant inside. So there is no pressure gradient. The PM is 85. You see how the pressure, the saturation of pressure is obtained. And then what we want to prove is that you can prove that for long times, if initial data had compact support, and you assume that you can go for a long time without any modification of our system, it will develop a circular blob that propagates with time. It will be active only on the part where the gradient of pressure is active, and in the middle there will be constant pressure and dead cells. And this is the explanation of the propagation that is typical of the people who do solid models for tumors. They try to solve every boundary problem. The problem for us is Laplacian P equals phi of P, and you get this Hill-Shaw rho productal. And the idea is that you are in several dimensions. But you know, there's a meta theorem that says that in several dimensions, where the geometry is a bit rounded at the tip, the Laplacian of P is like PRR plus n minus 1 over R PR, and this will go to 0 because this is not 0, PR is not 0, 1 over R goes to 0. So it's one-dimensional. And the last thing we proved is that if you solve the one-dimensional problem, this is a KPP problem more or less. And you can find the critical velocity that depends on a certain number, which is the integral of the production rate. So integrate the production rate, you get this thing, and the R prime is the speed of propagation of these monsters. Now, this is just a mathematical curiosity to say that our problem is a variation of KPP, one of the zillions of possible variations. We call KPP when there is a reaction, diffusion, and a constant speed of propagation at infinity. So we prove that this is true. In fact, in a talk 2 days ago, Yihong 2 did computations for Stefan problems finding these velocities. It is not what I do now, but the idea that this part of the proof has a traveling wave, has a velocity, is part of this beautiful ideology of finding traveling waves with constant speed and how many solutions go to them. Under our conditions, all solutions with compact support in our model, the first model, are monotone, and they have a tendency to go to the only possible solution, so this traveling wave is an attractor, which is not true for more general models. In the case of the nutrients, you don't get this theorem. So we don't know if for the nutrients you can prove this theorem. Can we? We cannot, right? Oh, this is important because this is an open problem. You should say thank you. Okay. Now, model with active motion. As a variation of these models, Pertam suggested to Fernando and 2 younger collaborators in Paris a variation where the things were not so rough, because they say, oh, let's eliminate all the difficulties of porous medium and try to put a smoothing by putting an ablation of rho. And then the proofs are easier, the result is easier, but when you try to work out the equation that is the typical Hill-Shaw equation, then this term that was your friend is no more your friend. So you have this stationary equation, which is a very ugly looking Hill-Shaw. If someone has seen this equation, we will be happy to know. Okay. So if you regularize, it will be good for numerical computations, but in some sense it destroys the simplicity of the theory and the phenomena that you want to see in the limit. And then there is a list of references that I will put on the web page. Okay. It is not comprehensive, of course, but in the paper there are many more. And I think that it is enough for me. Thank you all for your attention. Thank you.
Surely not the end.
Questions? So your uniqueness result seems quite strong because the pressure itself multi-value, right?
That is it. Yeah. But in some sense, the pressure tries to solve a nice equation. And we know that there is uniqueness for Hill-Shaw. On the other hand, it is tied to these remaining tails. I mean, the number of cells that are still waiting to be activated. So the only problem of the uniqueness that is natural in the model is how to prove it. Because the limit, the relation rho to P is singular. And this is where this duality method, Holmgren method, Hilbert duality method is very good. In fact, it's a beautiful technique for nonlinear problems. This is why I'm making some propaganda for this duality method.
Already it's there for shock waves.
Aha. Yeah, because it comes from hyperbolic people.
Yes, yeah.
We don't talk enough to the hyperbolic people. I say that because he likes it.
It came from 1960.
Yeah, 50.
Yeah.
Because Olenek and Carmen.
Yeah, and Olenek did the same. Yeah.
That's it. That's it. So it's a very useful technique in things where you cook up a duality expression. And then you have to use, this is where you use this regularity theory, existence of solutions for bad equations. All of a sudden you find that all of these things that you never wanted to learn is useful, because if you want to solve, if you are able to solve the dual equation, then you prove uniqueness. Which is, but you need existence in a very bad class to prove uniqueness in a not so bad class. It's a trade-off, right?
Why did you call that maximum principle type thing the Liao type inequality? I don't see the gradient there. Where is the gradient?
Where?
You have to go back to quite a few slides where you say that people in whatever call it the Liao inequality.
Oh yeah. The estimate that is called Liao are estimates like in porous medium flows. You have estimates that say, for instance, in porous medium you say ut equals Laplacian of um, and then you get that the gradient of minus 1 equal or larger than minus a constant over t. So, eliminate the t. So this thing allows you to say the ut equal or larger in a certain cu over t. And these type inequalities lead you also to make controls of the gradient of u in terms of c over t. And this is something that they did, Li and Yao, for evolutions, geometric evolutions on manifolds. But in the case of porous medium was done by Aronson and Beniland, and more or less the years were more or less the same. It was more or less 1979, more or less. And I wrote a paper with Laney and Lou and Villani, where we make the connection between these guys and these guys. So estimates, a priori estimates based on homogeneity considerations that tell you that something is bounded from below, and then you can get a certain Harnack because there is a bound from below.
Yeah, but Liao is much more than just homogeneity consideration.
The way you derive the inequalities depends on the structure of your equation. But inequalities tell you that a certain quantity that you...
What I don't see there is once you get the bound you wrote Laplacian of u to the m-1, is that what you mean on the top there?
Yeah, if you have the Laplacian here, what is bounded below is the Laplacian of u to the n-1. You never get a bound for this guy.
How from there you get the bound on the gradient? That's...
Oh.
Okay, well, I mean...
Okay.
If it's a long story, we'll tell you.
I can tell you.
Okay.
I mean, it's not evident, but the idea is, if you know the Liao, you discover that they do some estimates, and then they get bounds on the gradient a bit indirectly, but they get them, and this is what allows them to do geometric Harnack inequalities. Okay. Okay. Do you have another hour so that we can go? It's interesting for me.
Yeah.
Thank you.
So, before I just want to remark, I want to make a couple of announcements after we thank Juan Luis for his beautiful talk.